All right, welcome everybody to lecture 3. So just a few things before I get started. By now you should have seen that homework 1 has been posted, and that's going to be due this coming Thursday. And so in connection with that, remember that I have an office hour today today, Monday, from 2 to 3, and the TA Liang has an office hour tomorrow from I think 3 to 4. And then just to keep you updated, I'm in the process of getting another TA to do some problem sessions and extra office hours as well, but that's still being sorted out, but there'll be more details about this to come soon. Okay, are there any questions before I start? Okay, cool. So today I'm going to finish off a few applications from the theorem we proved in the last lecture. And then I'm going to go on and look at the complex numbers and some of their properties, as well as some basic properties of Euclidean spaces. So just to recap from, I'll also say that I'm experimenting with lecture delivery. So today I'm going to be using continuous screen instead of slides. I think that might work better. So we'll see what works better. Okay, so to recap from last time, the last theorem that we proved was given x larger than 0, there exists a unique real such that y to the n is equal to x. So I should say given x greater than 0 and a positive integer, there exists a unique real such that this equation is satisfied. And so we proved this. I'm just going to informally refer to this as the y to the n equals x theorem, because I'm going to use this theorem this lecture and the next few lectures. Okay, so a corollary to this theorem that you get is the following. So I'm going to let a and b be positive reals. And n a positive integer. And then the conclusion is that if I take the nth root of their product, this is just going to be equal to the products of the nth roots of each of them, okay? And so how do you do this? Okay, so you let alpha be one of them and beta be the other, okay? And then what I do is I compute their product, AB, so this is going to be equal to alpha to the n, beta to the n, and this is the same as alpha beta to the n, like this, okay? And so if we look at the equation, if we think about the equation, so over here, think about y to the n equal to AB, the theorem from last time guarantees that there's a solution and it's unique. And so we know that alpha times beta satisfies this equation and it's unique by the theorem. So thus, by uniqueness, given by the y to the n equals x theorem, we have, so the solution must be alpha times beta, and so we have ab to the 1 over n equal to alpha beta equal to a to the 1 over n, b to the 1 over n, like so. Yeah, so that's something that you basically get for free from the last theorem. Another application just of the supremum in general is decimals. So how to see real numbers as decimals. Okay, so I'm going to let x be real and positive. Okay, and what I'm going to do is I'm going to let n0 be the largest integer such that n0 is less than or equal to x, okay? And so such a choice can be made for this n0 by the Archimedean property that we proved last time. So by Archimedean property. So I can choose the first one. And so then inductively, it's going to be an inductive process. Okay, so having chosen the first k of them, so n0, n1, up to n to the k minus 1, I'm going to let nk be the largest integer, such that this inequality holds. So I'm writing things in base 10. Like this. Okay. And so what I'm going to do is I'm going to define a set, right? And the set I'm going to define are elements that look like this. So the first one is just going to be n0. The second one is going to be n0 plus n1 over 10. So just all the choices I've made, basically. n0 plus n1 over 10 plus n2 over 10 squared, and so on. Okay. And so what do I know about this set? Well, it's non-empty, okay? And it's also bounded above. Okay. So thus, the least upper bound property tells you.
Sorry, how did you choose?
Yep.
And how did you choose all of the integers except for n0?
Oh, so you're choosing them inductively, right? So I choose n0 first, and this base case is guaranteed by the Archimedean property. And so then the rest is an inductive process, right? So once I've chosen n0, then I can choose, here, I'll write it here. So you choose n0 first, such that n0 is less than x.
Okay.
This choice is guaranteed. And so once I've made this choice, then I choose n1, such that this holds.
Thank you.
So then I've chosen n0 and n1, and then you continue this process. Over 10 plus n2 over 10 squared less than or equal to x. Okay? Does that answer your question?
Yeah, thank you.
Okay, cool. So the least upper bound property tells you that the supremum of E exists. Okay? And you conclude, and so I want you to have a think about this, not now, but later. In fact, the supremum of this set is just X itself. Okay. And so the decimal expansion of the real number is X equals N0, N1, N2, N3, and so on. One way you can think about it is that if the X that you choose to begin with is rational, okay, the X that you choose to begin with is rational, this process here will terminate. It will terminate in a finite number of steps, and the set E will just have a finite number of numbers in here. If it's irrational, then it will be infinite. Okay. And then I'll just say here, it can also do this in the reverse direction as well. Okay. Okay, so I want to say a few more things about the reals. And so I'm going to talk about the extended reals. Okay, so the extended reals, which I'll denote by R star, are defined by the normal real numbers. And then I'm going to add in two elements. One is minus infinity and one is positive infinity. Okay. and such that how does the order work? Such that you have this. For every real number lies between these two elements here. For every x in the reals. So some observations are the following: is that so positive infinity or just infinity is an upper bound. For every subset of the extended reals. And so every subset has a least upper bound. Because if we were just working with the real numbers, for the least upper bound to exist, we need to take a subset that's not empty and bounded. All right, but here, if the set is not bounded, you can just take positive infinity as an upper bound. Okay. And then the same discussion applies to lower bounds. Okay. Another important observation is that the extended reals. Sorry. So R star does not form a field. Okay. I mean, we don't have inverses, for instance, for infinity. But it's not a field, but we do make the following convention. So so one is that if I take any real number, okay, and then I add infinity to it, this is going to be positive infinity, okay, for all reals, right? So x here can't be minus infinity. It has to be a real number, okay? Another one is if for all reals, I could subtract infinity and get minus infinity, all reals. Another property is that if you take any real number and you divide by infinity, or if you divide by minus infinity, you're going to get 0. And then we have the following properties as well, which governs the interaction of infinity with the order. So what do I mean by that? I mean, if x is greater than 0, then x by positive infinity is going to be positive infinity. And similarly, x by minus infinity will be minus infinity. And then 3 is just going to be the reverse. Is if x is less than 0, then x by positive infinity is going to be minus infinity, and the other way around, x by minus infinity is going to be positive infinity. So we have the following conventions to work with when we extend the real numbers, but we lose the field part. But you also gain that all subsets have a least upper bound. Okay, so I've been talking about the reals quite a lot, so I want to now build and talk about the complex numbers. So let's talk about the complex field.
Oh wait, sorry. Can I quickly ask a question?
Sure.
So for 2 and 3, does x have to necessarily be part of like only the reals, or can it be part of like the whole extended thing? Like, could x be infinity and this still applies? Does that convention still exist?
I mean, it's definitely, okay, yeah. So it's definitely fine to write this for x real, for x being plus or minus infinity. I think it should be fine. Yeah, I mean, it should be fine.
Okay.
The real issues occur, yeah, so the real issues occur when you try to divide infinity by infinity. They're the sort of things that you need to be careful about. Okay?
But I mean,
Okay.
don't you have like infinity times negative infinity in this second one here then? And then you would have like the opposite thing in 3.
Yeah, exactly. I've just stated it. Yeah, I've just stated it for real, for x being real, but they should hold for x being replaced by infinity and minus infinity as well. Yes.
Or like you would get different things. Right?
The issue, yeah. So the issue that I'm avoiding here, like the real issue with the extended reals is dividing.
Okay, yeah, never mind.
Okay. So for the complex field, so the definition. So a complex number I mean, just a philosophical comment, like based on the previous questions, is that I haven't, like in these axioms 1, 2, and 3, I haven't told you any law governing what infinity times infinity is, okay, or what a minus infinity times infinity is. So it's okay just to accept that we have these axioms just for the reals interacting with infinity, okay? That's all I've said. I haven't said anything about infinity times infinity. So in the system that we have right now, that's not defined, okay? Okay. It's an ordered pair of real numbers. So here, order, so when I say ordered pair, means that you can't just swap the places, right? So it means that A, B, A comma B is not equal to B comma A, right? Whenever A is not equal to B, okay? So the order of inside the tuple matters. Okay, so some things to note is that if I let X be A comma B and Y be C comma D, be two complex numbers. So I'll denote the complex numbers by C. So first thing is equality holds. So X is equal to Y if and only if A is equal to C. So the first slots are equal and the second slots are equal, right? And B is equal to D. And then if I take two elements, I need to tell you how they, what the addition and multiplication looks like. So if I add these two elements, I just add things component wise, like this. I'll call this star. And the second one is xy is equal to, so I need to tell you how they what the product is, okay? And so the product, right, I've got to think this is complex numbers, right? So the product is not going to be the naive thing where you just multiply each component, right? So A times B comma C times D. That's not going to be the multiplication law for the complex numbers, right? So the complex number, you should think about the second slot, like say here, as being the I component, and the first slot as being the real component. Okay, so the multiplication law looks like this. Okay, and so we have a theorem which I'm not going to prove. so the definitions are star and star star. Turn a set of all complex numbers into a field. And in this field, the additive identity is going to be 0, 0. And 1, 0 is the multiplicative identity. Okay. And so for the proof of this, it's just going to be, it's just going to be verification of the field axioms, which I'm going to spare all of us. Okay, see textbook. But I will point out something interesting. So I guess the question I want to ask is, if I take a complex number that's non-zero, right? What is the multiplicative inverse? Does anyone know? So it's not going to be 1 over A comma 1 over B, because that's not how the multiplication law works. So really we need a formula that basically inverts this, okay? So I'll tell you that the multiplicative inverse should be something that looks like this. A over A squared plus B squared, and minus B over A squared plus B squared, okay? And so a little exercise to do if you get bored is check. All right, so the theorem, so another theorem is we want to see the real numbers as a subfield. Oh, also, I'll just make clear that I've stated a theorem in which I stated a theorem in which I've declared that or claimed that the complex numbers are a field, right? But I've said nothing about order, okay? So there's a homework problem about putting an order on the complex numbers and seeing whether that order has the least upper bound property or not, okay? So you'll see something like this on the homework. Okay, so we want to see the real numbers as a subfield of C. So how do we identify the real numbers in this complex number setup that I've got here? So the way you do it is you basically you see the reals in the first slot of the tuple, okay? So for A, B in the reals, we have A plus 0, B plus 0 as being A plus B comma 0. And if you just multiply elements that only that have non-zero, that have the second component 0 in each of them, then the multiplication law above, this one, star star, just specializes just multiplying the first component. Okay, is going to be AB comma 0. Right, and there's nothing really to check here apart from the multiplication law. So this means R sits inside C as a subfield. Okay. So one thing that I should clarify now is we kind of all know the complex numbers is something that looks like a plus bi, where I is the square root of -1. Okay, and so now I want to identify the construction here with what we already intuitively know. Okay, so we want to now want to make the identification of a comma b with a plus bi. Okay. So the first thing to do is we've seen how the A part, so the reals, we've seen how they kind of sit inside C, right? How we identify the reals with elements of the complex field we've just constructed. It's just all occurring in the first slot or the first component. Okay. So so the next task is, okay, how do we identify I? Okay, so we're going to make the definition that I, right? So here I is the square root of -1. So how do we identify this element in our construction? And so what we're going to do is we're going to set that to be 0, 1, like this. Okay. And so the theorem is that I squared is equal to -1. And so the proof, so how do you see that I squared is equal to -1?
Is it the multiplication law for those numbers?
Exactly. Yeah, exactly. You need to use the multiplication law for complex numbers. Okay. So this means that I squared is going to be 0, 1 multiplied by 0, 1. Okay. And then if I scoot back up here and see the multiplication law and perform it on this product, you're going to get -1, 0, like this. And then, but in the previous theorem here, we identified the reals with the first component, right? And so now I've got -1 in this first component and 0 in the second component. So that's the proof. And so once you've built all this, then you can actually write down and say that if I take two real numbers, then a comma b is equal to a plus bi. Okay, and so the proof is just a calculation again. Right, so that's a plus bi is equal to a comma 0 plus b comma 0, 0 comma 1 by definition. And so then we leave the first thing alone, and then we use the product law on the second, and you get 0 comma b, and you get exactly ab, like so. So another definition is the conjugate of a complex number, right? So now we're justified to go between a plus bi or a comma b with the multiplication law. Either one is fine. So if a, b are in the reals, and I take a complex number a plus bi, then the complex conjugate, so then we set z bar to be equal to a minus bi, is called the conjugate or the complex conjugate of z. It's called the conjugate of z. And then a little bit more terminology. So we say a is called the real part. Of z. B is called the imaginary part. We'll see. And so sometimes you might see notation that looks like A equals the real part of Z, and B equals the imaginary part of C. I'll probably say right now, I think I prefer this continuous scrolling for the notes. So if there are any serious objections, just let me know by email if you want. But I think it's going to be better. The reason I decided to change is that we probably have some longer proofs now for the rest of the class. So it might be easier just to scroll rather than have slides. Okay, so we have a theorem. So if I take two complex numbers, then the following whole. Z plus omega, oh, sorry, Z plus W. If I take the conjugate, it's the sum of the conjugates. Same with the product. If I take the sum of two conjugates, I get double the real part of C. And then if you take the difference of the conjugates, you two times the imaginary part of C. So, and then the last one is the quantity Z by Z bar is real and positive, except when Z equals 0. Okay. And so the proof is pretty straightforward. It's just using the definitions above. So I'm going to omit it. So exercise. I guess one thing to point out that might be useful is that if you compute ZZ bar, this is equal to A squared plus B squared. Be helpful to note. Okay. And so now, actually, now that we have this theorem, we can actually make another definition. Okay, and so the definition is if Z is a complex number, then we're going to set, so then the absolute value of Z, or the norm of Z, is the non-negative square root of ZZ bar. So this is actually quite subtle. Okay, this is a subtle point because first of all, the theorem, so 0.4, so actually we've got to think about the equation. So think about the equation y squared is equal to ZZ bar, right? So 4 above tells you that ZZ bar is real and positive, okay? And then the y to the n equals x theorem tells you there is a unique non-negative square root. Which is the norm. All right, so another theorem listing some properties of the complex numbers. So ZW in C. Then what do we have? So one is the norm is positive unless Z is equal to 0, in which case the norm is 0. 2. If I take the norm of the conjugate, that's the same as the norm of the complex number itself. Another one is taking the norm of a product is the same as taking the product of the norms. And that the absolute value of just the real part is going to be less than or equal to the norm of the complex number. And then the last property is that, and so this is going to be actually one of the most important properties, is that if I take the norm of a sum, this is less than the sum of the norms, right? And so this is the famous triangle inequality. And this notion is going to be very important for us for the rest of the semester when we look at metric spaces. Okay, so this is important later. And by later, I mean very soon, in the next few lectures. So important later for metric spaces. Why is it called triangle inequality? Well, if I have a triangle with two side lengths or two vectors z and w, and this is z plus w, then it says that the length of this side is less than the length of this side plus this side. Okay, so I'm not gonna prove 1 or 2 because they basically follow immediately. I'll just quickly do 3, 4, and 5. So for 3, so if I can set z to be a plus bi and w to be c plus di. Okay, and so then if I compute the norm of the product, if I take this is going to be something like ac minus bd squared plus AD plus BC squared, oh, sorry. AD plus BC squared. And then if you expand out and refactorize, you can check that you get A squared plus B squared multiplied by C squared plus D squared. And this is indeed the norm of Z squared and then the norm of W squared, like this. So we just proved what did we prove? We proved that the norm of ZW all squared is equal to ZW all squared. So by uniqueness from the y to the n equals x theorem from last lecture, we have the norm of ZW being equal to the norm of Z by the norm of W, like this. Okay, so for part 4, just using the axioms of real numbers, you can observe that a squared is going to be less than 2a squared plus b squared, and so hence the norm of a is equal to the square root of a squared, which is less than or equal to the square root of a squared plus b squared. All right, and so for 5, actually, I'll have the proof of 5 will be in the notes, but I think I'm just gonna, I think I might skip it because I'm running out of time and I need to get through some other things. So exercise or notes or textbook. Okay. So another important thing too, not just for this class, but in general, is the Cauchy-Schwarz inequality. Okay, so what does it tell you? It tells you that if you have complex numbers like this, and then other complex numbers. Then the following inequality holds. The sum from j equals 1 to n aj bj bar all squared is less than this. So what this inequality, one of the main uses of this inequality is that if you have a sum of products from a finite sequence, and that you're trying to bound in absolute value, then the Cauchy-Schwarz inequality tells you that you can actually break them up. Okay, with inequality, of course, this is not equal in general, but you can write it as a sum of squares multiplied by another sum of squares. And so a lot of the times this inequality is very, very helpful. And the proof, again, I've got, I've written out here in the notes, so I can put them offline, but it is a calculation. So I'm just going to put C notes or textbook. But it is, it's just a calculation. Okay, so for Euclidean, okay, so next important thing is Euclidean spaces. So this is kind of going to be a prelude to metric spaces. So the definition. So for a positive integer, I'm going to let, so I'm going to let Rk be the set of k tuples of reals. So x1 up to xk. Like this. And so the elements of this are called vectors. And you can either denote vectors by a boldface or a tilde. It's a little hard to do boldface when you're writing, so I'm just going to use tilde. So, so a few observations is that, so if I have this vector, so this is what I mean by tilde. And x, what's the sum? So I have a sum x plus y is equal to x1 plus y1, xk plus yk. This. And then I can also scale too, right? So I have alpha times a vector as being alpha x1 up to alpha xk for alpha real. And so, thus, if you take so the space is closed under addition, so sum of vectors is in Rk, and multiplication by scalars is in Rk. Okay, so you know, all the obvious axioms hold for this. So what do I mean by that? I mean that addition, so addition of vectors and scalar multiplication satisfy commutativity, so all the good stuff, associativity, and distributive laws. And so it turns this space, turns Rk into a vector space. Over the real field, because that's what the scalars are here. Okay. One other very useful operation on this is the dot product. Okay, so definition. Dot product. So take x and y. We can define the dot product as x dot y as being the sum from I equals 1 to k, xi, yi, like this. And the norm by this. The square root of the dot product. And then this is the sum from 1 to k, xi squared, half like this. So kind of introducing all the things that we've used in calculus. And so then there is one theorem, again, outlining all the properties of this space with its norm. So I'll write this out. Suppose suppose I have three vectors in Rk, and I take a scalar. Then the norm is always non-negative. 2, the norm is 0 if and only if the vector is 0. 3, if I multiply a vector by a scalar and take the norm, it's just going to be the norm of the scalar by the vector. The dot product, if I take the norm of a dot product, it's the less than the norms multiplied. Again, we see our friend the triangle inequality, again, very important. So this is x plus y. The norm is less than or equal to x plus y, like so. So we had this for the complex numbers. We also have this for Euclidean space. And then 6, which is really a consequence of 5, just by substituting different vectors, is that if you take the norm of x minus z, this is going to be less than or equal to the norm of x minus y plus y minus z. Also, point out here that this trick, very important. So when you want to estimate the distance between two things, introducing a third thing, and then, so the trick x minus z, we're going to use this trick over and over and over again for the rest of this class, is that if I want to estimate something that looks like this, I'm able to write this as x minus y plus y minus z for any y, and then use triangle inequality like this. Very, very important. Okay. So the proof of this, again, is just properties, see textbook. I do have a little bit of time left, so I think I'm going to go back and prove the Cauchy-Schwarz inequality. Before I do that, are there any questions?
Yeah, so is the main difference between the complex numbers and R2 the way we define multiplication?
Yeah. The other thing about RK as well is that it's not a field, right? So yeah, I mean, there's this, yeah, you have a notion of combining vectors via the dot product, right? But there's no good inverse for this.
Right, okay.
Yeah. But but the additive structure is fine. But yes, exactly. The product laws are very different. Are there any other questions? Okay, I might just quickly jump back and prove the Cauchy-Schwarz, right? So let's just go back. So Cauchy-Schwarz says that if I take a sequence of n complex numbers and I take another sequence of n complex numbers and I'm trying to estimate the sum of their products, their pairwise products, then this is always less than or equal to the sum of squares of each of them. So I can separate them in some sense. So proof of, so time left over, proof of CR inequality, sorry, CS inequality. So how am I going to do this? Okay, so I'm going to assume, so set A to be the sum of squares for the A sequence. I'm going to set B to be the sum of squares for the B sequence, and then C to be the sum of the products AJ, BJ, bar. And without loss of generality, assume B is non-zero. Otherwise, the claim is trivial. And what are we going to compute? Well, we're going to compute with something that we know to be positive. Okay, so 0 is always less than or equal to the sum of non-negative things. So I'm going to sum over J, and I'm going to have BAJ minus CBJ, like this, squared. Okay, where A, B, and C are these quantities over here. So I'm just going to expand, but the way I'm going to expand is by multiplying each element by its conjugate. Okay, so this is going to be the sum equal to the sum over J of itself. And then I'm going to take the conjugate of the whole thing and then distribute that over the subtraction. So this will be BAJ bar minus CBJ bar. Note here that I didn't put the bar above B. I can forget about it because it's just real. B is real. Okay. And so then if I expand this out, what am I going to get? I'm going to get the sum over J of BAJ bar minus the sum over J of BAJ CBJ bar minus the sum of CBJ BAJ bar plus the sum over J CBJ bar. And now I want to write this expression in terms of the quantities that I initially defined up here. Okay, so in the first sum here, B doesn't depend on J at all. Okay, so I can move that out the outside. So I can have B squared, right? And then AJ and AJ bar makes AJ bar the norm of it squared. So it's going to be this sum of J AJ squared. But then I've defined that to be A. So that's just going to be A. Okay. And then similarly with the other terms, it's going to be BC bar sum over J AJ BJ bar minus BC sum over J AJ bar BJ plus the norm of C squared sum over BJ squared, like this. And then the thing to realize is that, see this quantity here and this quantity here. Oh, sorry, I should just have it around this. So one of these sums is C and one of them is C bar. Okay, so then this becomes B squared A by B C squared minus bc squared plus c squared b. So I get b squared a minus b squared by the norm of c all squared. And then if I factorize, I get b minus b norm of c. And then remember that the initial thing was positive. So I conclude that b by ab minus b norm of c is greater than or equal to 0. And then since b is greater than 0, because remember I made the without loss of generality assumption at the start, this implies that ab minus c squared is greater than or equal to 0. And this is if you rearrange this is the same as the claim. Okay, that gives the claim. Okay, I think I'm going to end there. Are there any questions at all?
I had a question about the proof of the triangle inequality.
Oh, I don't think I proved it. Oh, I didn't prove it. I didn't prove this.
Oh, okay.
So.
Oh, yeah. Sorry.
Sorry. Yeah. Okay. So the proof. Yeah, I never proved the triangle inequality. You can see it in the. Yeah. Yeah. I never proved it.
Okay.
So you can.
Yeah, it seemed like there was one of the proofs relied on like the fact that like the square root of a bigger number is larger than the square root of a smaller number, and I was wondering like where that.
Oh, that's a good question, actually. Let me see. Yeah, it's concluding that the norm is monotonic, right? Yeah, that's your question. Let me think. Oh, you can conclude that by, I think if you know, in the first line of the proof of the y to the n equals x theorem, we made like a comment, this was previous lecture, we made a comment that if you know that y1 is less than y2, then y1 to the n is less than y2 to the n. And you can use that here. Does that clarify things?
Yeah.
Yeah. Okay. Any other questions? All right, I'm gonna end here. Have a good rest of your day, and I'll probably see some of you in office hours this afternoon.
Thank you.
Thank you.
Thanks.